Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth. Hello, folks. Today we are joined by Dr. Craig Przybyla to discuss the Engineering Scientist Exchange Program, AFRL's Composites Performance Team, and why ceramics are such a hot topic in aerospace.
In 3, 2, 1.
Dr. Craig Przybyla, welcome to the podcast.
Thank you. It's fun to be here. I'm excited.
Yeah, we're glad to have you here too. And for our listeners, we all know that a lot of great aviators and inventors are tinkerers. You know, you can go back to the Wright brothers, which, Craig, I know you didn't invent the airplane or anything like that, but you're inventing other things. But we know that you're a tinkerer too. Can you share with us some of the things you like to work with?
I have always really loved to work with my hands. I remember even as a young kid, I watched this show, Rescue Rangers. I don't know if you've ever seen it. It's kind of a 80s, early 90s thing. And in the show, these chipmunks, they make these airplanes and everything out of like household junk, like bottles and old stuff. And so I remember as a kid, after watching the show, I'd sit down at my little desk in my room and I'd make these like flying airplane things for chipmunks out of bottles and stuff like that. That was when I was really young. And then as I got older and more interested in teenage things, one of my first major projects was my dad. He bought this really old, it's like an 83 Subaru hatchback. And this was probably like 95, 96. So it was a pretty old car at the time. And the paint was just thrashed on it. And so I basically by myself stripped the whole car. And then we took it down and got it painted. And then I put the whole car back together again and with like a new radio and like spice things up a little bit. So it wasn't so ugly and not cool for a first car. And then that was my car when I turned 16. So I started that project like 15 and then I finished it just in time so that when I got my license, I had a car. So I've done tons of projects like that, throughout my life. So just fixing things and tinkering and doing different projects.
I think the Chip and Dale, the Rescue Rangers, if I'm recalling if my memory is serving me right, they would be proud of you.
Yeah, they were pretty cool flying machines. They never tried them out, unfortunately, but I thought they were pretty cool.
So. Well, I have to know that. Do you have a favorite, Chip or Dale? Who's more inspirational?
I guess Chip. I mean, he was the natural leader, right? Dale was
That's how I saw it, yeah.
Yeah, the dorky follower guy. So, yeah.
Hey, that's what you got to have a best friend like that. And also, follow up then. I got to know, when you actually souped up the car, did you add in a 6 CD like changer? Like what really made the sound system like? Let's say, what made it cool enough when you were 16 to drive?
It was definitely a nice CD player before we tore out the old tape player and put in a CD. My kids don't even know what CDs are these days, but and the face, I think, turned over when you turned on the car. It would like be this theft-proof, innocuous screen, and then when you turn on the car, like flipped over and all these fancy lights came on, and it was like totally awesome.
That's like you're driving around like Kit at that point. That's super cool. Yeah, because I had one that didn't quite have that addition. I just had the 6 CD changer, but my wife's car did have a face you could move, like a radio that was hiding CDs. So that's
exactly.
I love that. So I'm curious then, with how much work you've had working in cars, the past and tinkering, do you still do that today? Or you kind of still a gearhead, if you will, or just tinkering with like microelectronics? Like, what do you do at home?
I have a big family. I have 7 kids. So like things are breaking a lot around our house. So most of the tinkering I do today is just fixing things that get broken. So we have like boring cars, but they need repair and maintenance. And I have older cars because I have a big family. I can't afford new cars. So a lot of things just like changing brakes and fixing knobs and lights and other things that get broken, or door panels or whatever. And so I do the same thing around the house too, like broken walls and doors and cabinets and bathroom fixtures and all sorts of stuff. So right now I'm more of a repairman than anything else.
But you have the skills in place to do it. So at least you're keeping that in practice, though. The repairman role is an essential one.
Absolutely. A lot of it is to not necessarily buy something new, but like come up with an ingenious way of, fixing something with what you have available. So that takes some ingenuity, probably.
Oh, of course. So with that, now we have kind of an idea of who you are as a very hands-on, a tinkerer, somebody who loves some of the very material world. Let's kind of go into your training that kind of brought you up to this point. So we know eventually a material science class really hooked your attention in school, but beforehand you were in pre-med studies. So what really lured you into that kind of that trade? What made you want to do pre-med?
Yeah, that's a good question. I really enjoyed biology in high school, and I always thought a doctor would be a cool profession, being able to help people. And also they were all the doctors I knew were rich. So that was cool too. So I came into my undergraduate studies. I started in 98 as a freshman at Brigham Young University, and I took this 5 credit biology class, and it was every morning at 8 a.m. and it was just not my friend. I don't know. I lived in the dorms and it's crazy and no one goes to bed at a decent time. And so at 8 a.m. biology class every morning was rough for me. And I also realized a lot of that line of study, although interesting, was memorization focused, which was not really my strong suit. I really much more enjoyed solving problems, which was not what a lot of the early curriculum was for. Like, I was a microbiology major, at least for that semester. And a lot of that was just, memorizing facts and processes and stuff like that. And I wanted to do more like problem solving. And so I started looking at engineering and took a intro to like mechanical engineering class, which went through a bunch of different potential fields within mechanical engineering, materials, thermodynamics, robotics, and so forth. And just really liked the idea of all these problems. And so I started taking more mechanical engineering classes, and then eventually actually fairly quickly switched over to a mechanical engineering major, and just really liked the curriculum, which was much more focused on, they taught you the fundamental theory, but then you spent most of your time applying that theory to solve different problems. And that's really where I enjoyed the challenge, was taking my knowledge that I had and then applying it to solve some type of challenge or problem.
And I can definitely feel and reflect in that because I did some early science level courses back in my college, like when I was in college. And same, where I was like, this is more memorization, like cool and all, but I want to be more practical with journalism, especially in the field. Like I want to be doing this, writing it, speaking to the people. And I, again, completely see that viewpoint. I'm glad you found more of what you were looking for, especially with materials work and eventually, mechanical, all that business with engineering. So I'm curious then as you're moving along. So I know you eventually went to get doctoral work done at Georgia Tech. That's how you first made a connection with our materials lab and manufacturing directorate, I should say. So what was the first project you took part in there? And what was that connection process like? Were you given an offer? Did somebody recommend you? Walk us through that process.
Yeah, that's a good question. I need to step back though, because it really started, you mentioned this material science class I took my sophomore year, which was basically introduction to material science through the mechanical engineering department. It was an interesting class focused on the different material classes, metals, composites, and ceramics, and polymers and stuff. In life, you have these moments that change everything. And so in that class, there was one lecture where at the end of that lecture, the professor got up and basically just gave a spiel, kind of an introduction to research, and said, we've been talking about materials and, how they're used in application, but there's also an aspect of this research related where you can go and look at new discoveries in materials. And I'm looking for researchers. And so if anyone's interested in this, go ahead and apply. And that moment shaped kind of the entire trajectory of my career, because I may have been half asleep in the class at the time, but then for whatever reason, he said something that caught my attention. And so I did apply, and it ended up being 2 people from that class applied, me and my friend at the time, Eric. And we were both kind of competing because he said there was one job, and, we didn't think he'd hire both of us. And we were both pretty top students at the time. And we were surprised that he actually hired both of us, which was great because we started as undergraduate researchers, and specifically his focus, that professor, his name was Dr. Brent Adams, and he did a lot of work in terms of crystallography and automated characterization of metals and metallic systems. And so I ended up spending the next 3 years of my undergraduate until I graduated is doing as an undergraduate researcher, getting my own project. actually writing a publication, going to a conference by my senior year and publishing that, and then staying with that professor to do a master's degree where I did a thesis with him. And then I, as you mentioned, got accepted to a PhD program at Georgia Tech, which was kind of through his recommendation. And so I ended up going to Georgia Tech and kind of continuing in that field, looking at fatigue of high temperature metallic systems, which is how obviously I got then connected with Air Force Research Laboratory, because my professor at Georgia Tech at the time, his name, Dr. David McDowell, had some funding from AFRL. Some of the government researchers from AFRL came down. We presented our research, got some feedback from them. And then as I was in a stage of my life where I still had no idea what I wanted to do, I knew I liked solving problems and engineering was great, but I knew someday I couldn't stay in school forever and I had to get a job. And so I asked the researchers, they're actually both still here at AFRL, Dr. Mike Caton and Dr. Mike Uchik, and also Dr. Steve Ross, which are all still here at Materials Directorate, about internships and what a career was like at AFRL and what it was. I'd never heard of Dayton, Ohio or AFRL or any of that. And so they said, well, why don't you come up and do an internship? I said, that would be great. And so I came up and did an internship in the summer of 2007, focused on what they were interested in, which is fatigue of these high temperature metals. And the rest is kind of history in terms of how they invited me back to finish my PhD there. And I've been, I guess I should say, here at AFRL, and I've been here ever since.
So let's go back to the work that you had, especially with our materials and manufacturing directorate. So you mentioned a lot that's high stress work, especially with materials. Did that kind of work in your early studies, in your internship, ever turn something bigger? Was this a simulated work, I should say, that's continued to go on? Has a project come out of this? Can you kind of walk us through what that was like? And again, any of its legacy you've seen kind of pass on?
Yeah, that's a really good question. So my early experience, right? So I mentioned I was focused on fatigue of metals. And so for my PhD, which I did end up, I spent the last 2 years of my PhD in the metals branch here at AFRL, and it came up with a unique probabilistic approach looking at how the local microstructure or the local structure, if you will, within metals affects how fatigue, which is basically cyclic loading of a material over time, develops into eventual cracks and then ultimate failure of this, which is what we're trying to avoid, obviously, right? So we want to be able to predict how this damage evolves over time so that we can set appropriate maintenance schedules and stuff like that to avoid these things from happening. And so we came up with a nice probabilistic model, and by the time I was done with it, I honestly wanted to change, right? And so I ended up, after finishing my PhD, I was an intern essentially. And then my first full-time position at AFRL that I applied for and was actually accepted for was in a completely different area. It's in ceramics. But that being said, it was encouraging to know that a lot of that early work that I did, I helped collaborate on some other projects from the metals branch that was leading towards some solutions to some real world problems with the current system that they had. But we had a aircraft that was having some fatigue problems. And so we were able to leverage some of our understanding from these probabilistic models, specifically focus on extreme value probabilities, which is a whole class of probability theory. And the metals team took some of that know-how, applied it to this problem they were having on this Air Force system. And it really helped to guide some of that work to help solve some of these issues. And so that was encouraging that some of the early work I did, which was AFRL funded, which not only got me here and involved, but also later transitioned to help solve a real problem that they were having on the metal side. Even though I went and took a different turn, that work was still there and progressed on.
It is great to see your work directly impact the warfighter, whether it's a new technology or a safer technology. That has to be really, really rewarding. And we're inching closer to asking you about your current job with AFRL as a composite performance research team lead. But first, I want to key in on something that you mentioned just a bit ago. it was about ceramics and your work there. So one thing we love to do is kind of do a little 101 for our listeners to dive into a topic. So could you give us a little 101 about what makes ceramics so special in the aerospace world?
Absolutely. Yeah. I mean, when most of our experience with ceramics, I guess the average person's experience with ceramics typically revolves around, I don't know, dishes, right? Like coffee cup. That's a ceramic. And most of that experience isn't necessarily good because if you drop it or they chip or they break easy. And that's the challenge we have with ceramics is that they do have a really nice high temperature capability. I mean, you could take that coffee cup and throw it in the oven and put it on 500 degrees for hours and it'll be fine, right? But if you drop it, as you're taking it out of the oven, it'll crack into a million pieces. And so we like the high temperature capability of ceramics, and we need that capability because we are doing a lot of things in very harsh environments. You think of the inside of a turbine engine. These things run at thousands of degrees Fahrenheit, or you think of a space, rockets that are sending satellites up. You have things at the propulsion, the rocket side, where you're actually burning the fuel that are getting extremely hot, or if you have reentry vehicles coming back into the atmosphere after having gone out into space. So in all these cases, the only way that we can survive a lot of these environments is to use ceramics, which have this really strong covalent bonding, which allows them to withstand very high temperatures without these bonds essentially disintegrating. However, they do have that effect that if you do get a damage, like a crack or something, due to the fact that there's nothing to arrest these cracks, there's no ductility, as we say, which causes bending, which allows these cracks to blunt and arrest. But in a ceramic, the cracks maintain a really sharp tip, and so that allows them to grow very quickly, which there's nothing to stop them. And so what we've done over the last several decades is we've developed a new class of ceramics called ceramic matrix composites, which add essentially interfaces within your material by using continuous fibers to reinforce them. So a lot of your listeners are probably familiar with like carbon fiber, epoxy composites. So these are like your plastic-based composites used more at normal temperatures. A lot of them are in golf clubs or rackets or bikes and stuff like that. But they also are used extensively as aircraft structures, as wings and stuff like that. And that fiber reinforcement for the polymer composites gives them strength in the directions that you need, and so it really tailors the properties. But in ceramics, we add those fibers because they not only provide strength, but they also provide features where damage will arrest, meaning it will stop and not zip on through the material. And so if you take a ceramic matrix composite coffee cup and you drop it, you'll get a little chip in the corner, but the rest of the cup will maintain its structure and integrity and be able to continue to perform its function. So a lot of the work that we've done in ceramics and composites in particular has been focused on these high temperature composites that allow us to have that high temperature capability, but also avoids that brittleness that you get with a traditional ceramic. So there's a very quick 101 of why we like ceramics, how we've modified them to work for important Air Force applications, and why that works well for us.
Thank you. No, that's phenomenal. So it gives us a great idea of why these are important, how they're used, and like you said, even some of the evolution that people would be comfortable or would know about. And the only other thing we are wondering too is that this actually kind of ties more into what your current work is. So we're going to introduce what you're doing now to revisit this question I got. So first and foremost, can you kind of break down for our listeners what it means to be the research team leader at our Materials and Manufacturing Directorate in the Composites Performance Team?
Yeah, so the research lead is a particular position that we developed in the Materials and Manufacturing Directorate to kind of oversee the in-house research that we do in particular areas, right? So as you mentioned, I'm the research lead for composite performance. So I oversee a team of about 8 government engineers And we are all focused on developing new methodologies and technologies and approaches to predict and to understand and characterize the performance of composites in application relevant environments. And so when I mentioned composite, that includes the broad category of the two things I mentioned previously, everything from the polymer-based composites, which typically involve a carbon fiber embedded in a polymer-type matrix like epoxy, all the way up to what we term as our high-temperature composites, which typically consist of ceramic fibers embedded in a ceramic matrix. And so my team that I oversee does a lot of in-house work on not only characterizing the structure of these materials, but also doing a lot of relevant testing at temperature and in the simulated environments that these things would see in real applications, like within a turbine engine or at the end of a rocket or something like that, and really try to understand to a high detail the behavior so that when we design and use these materials in real systems in the field, we don't get any surprises, right? We don't get anything happening that we have not designed for and not anticipated, and which allows our systems to work, flawlessly without having any problems in service. And so we specifically focus on how to test those, how to characterize them, and then also how to model that using computer simulation so that when we take our results and our models to design real things that we care about, we don't get any surprises, basically.
And you hit the nail right in the head. And the thing I was going to bring back around was, how do you guys actually test and model a lot of this at scale? Because I can imagine that if you're given a material, you could do it in a very small case, then scale that up as needed. But where are you in that process? Are you more of, like you said, the early characterization? We're going to test a centimeter like large section of this to make sure it works? Or are you doing full sections of aircraft to make sure it works or goes through?
Yeah, that's a good question. So in the materials directorate, we primarily focus kind of at the coupon scale of the material and the performance. And then we collaborate a lot with our aerospace systems directorate, also called RQ. And they are more the full scale in terms of like a wing or a fuselage or some type of actual aerostructure. And so we're kind of at a scale less than that, but a lot of what we do is very relevant at the scale that our aerospace systems directorate is working at. And so we collaborate very closely, where we provide materials and material behavior and fundamental response data to them that they then use in their structural type simulations. And so it's a very collaborative relationship in that regard. But our primary focus is at the kind of material scale, kind of the coupon scale. And to add one more point to that is, my team is the performance team, but we work very closely with the other teams in the composites area, which are the materials and processing team. So they kind of make the materials, and then we help with the performance characterization of a lot of those materials.
So really, from start to finish, with working a lot of these materials, your team has their hands in there, and you're seeing really all this go through its stages. The fact you're also interconnected makes it easier. So one person adds like, hey, I saw an issue pop up here. You have all the right minds on set, if you will, and on base. So that's really cool. You're also close to each other to make that magic happen.
Yeah, absolutely. And a great part of AFRL, and since I say this sincerely, not just as a sales pitch, but we really do work well together. The way that our budgets are structured and that our organizational structure is not a competitive relationship, but a collaborative relationship between directorates and what we're trying to accomplish to get the mission done, which has been one of the reasons why I'm still here after 15 years. It's just been a really fun place to work, very collaborative environment.
But going along that kind of idea, then you talked a lot about different testing ideas coming in from, whether it be in aerospace, literally in space, here with an atmosphere. There's a lot of folks, I'm sure, asking to test or build materials. So can you kind of tell us the balance between tech push and tech pull requests from those that either come from in-house for AFRL or outside the fence, if you will?
A big part of our mission at AFRL is, as I view it, and I think most would agree, is that we're kind of in the center of this center area between an industry making a design of a new system, say a new airplane X, versus what academia is doing and the basic research arm of the Defense Department is doing is coming up with new widget A, which will give us this revolutionary capability, right? And so we really have a mission of having awareness and also participating in this basic research where we're developing new things and new capabilities that we've never even thought of before, right? Such as a new composite ceramic that has a capability unheard of before, either temperature or performance or whatever. And then educating our industry essentially so that they're aware of this capability and they're able to have confidence to use it when they are coming out with the next system, the next great system for the defense of our nation. And so our role really is not only to identify promising technologies or to come up with them ourselves organically from in-house, but to transition them in a way at a level that then the broader, defense acquisition community has confidence that, okay, there's this new capability, we're confident that it's going to work, and we're going to use this in our next design. And so we do a lot of that, where we collaborate a lot with academia. We sponsor student projects supporting some of these new emerging things, just as my example that we already mentioned in my work in probabilistic theory of fatigue in metals. It was more researchy. A lot of that theory had never been thought of before. And then being able to use that to solve a problem that the Air Force had later on a real system is really our niche, if you will, where we can have that perspective that allows us to draw these things up when they're needed or when that capability will provide that additional advantage that we need to maintain the defense of our great nation.
I'd love to dive into one of those successes that your ceramics team has had from collaboration, and that would be the SWIFT program. Could you talk to us about that?
Yeah, so the SWIFT program is a new program that I am working on. I'm the program manager for it. It's actually what we call the BAA, just went out a few weeks ago, which is an exciting stage where we go out to industry and we call for proposals for them to propose solutions. But essentially, this is more on that side of the development arm where we're starting to really transition technology to make it ready to where we could use it on the next Air Force system. So SWIFT is specifically targeted for scramjet technology for hypersonics. So really trying to increase our ability to provide that high temperature scramjet technology capability that will power our future hypersonic systems. And so the specific technology that we're focused on for SWIFT is to develop a scramjet structure, isolator structure, which is entirely made from ceramic composites. And so there's several advantages to that. A lot of the current state-of-the-art scramjet technology is based on metallic systems, and some of the disadvantages of metallic systems. I was a metals guy. Hopefully they don't shoot me, but there are some disadvantages of all materials. In particular for scramjet technology, metals don't have the temperature capability necessary to get there. And so a lot of them require active cooling during operation, which can become very challenging when you're pumping a cooling solution through this structure at the same time where you're literally burning fuel through it at Mach 5 or higher speeds. And so by transitioning to a ceramic isolator, we'll allow ourselves to operate using no cooling, which will greatly simplify the system. Additionally, the ceramics that we're interested in are much lighter than the metallic systems. And so they'll provide much better range and even payload capacity than a hypersonic with this scramjet that is made out of a metal. So what we're doing in the SWIFT is we're going to demonstrate this capability. We've done a lot of work in developing the relevant ceramic matrix composite systems. We've also already done a lot of work in terms of characterizing the performance of those systems. And now we're ready to do a full demo of this capability so that we can prove to the system designers out there making the next great hypersonic vehicle for the Air Force or for the nation that this technology is ready. And so that's what SWIFT is calling for. It's calling for a full-scale demonstration of a ceramic matrix composite isolator for a scramjet engine. And so we're very excited about this program.
Oh, absolutely. And we've talked to folks about scramjets, about the future looking back to the past, if you will, for what we're going to be doing for hypersonics and beyond. So to know that you're actually on the ground there working the material is brilliant. And the fact that there's so many benefits to working ceramics, I mean, it really does sound like this is going to be exciting. And I'm sure the metals community will give you a pass on this one.
Mm.
I think they may agree. We're going in the right direction. Speaking of like really cool programs, though, there's kind of something you had a chance to do that just fascinated me. I'm a somebody, if you've listened to the podcast, who loves to travel, see the world, and it turns out you got to do that in an even cooler way than I did, which is working as part of the Engineering Scientist Exchange, or ESEP program. So, what is ESEP, and how is it important to the AFRL mission, or how does it kind of play in?
So this is a gem, actually, and I appreciate you being willing to talk about this, because this is something that's also been one of those life-changing moments that I talked about. So the ESEP program is one of the many opportunities that Air Force civilian engineers have through the what we call the Developmental Education Program call, which comes out once a year. And in that call, there's different opportunities to grow and advance and career broaden. And Engineering Scientists and Exchange Program is specifically focused on going overseas to an allied nation. There's 16 current countries that participate in this program, and you actually sit in a military government lab of that allied country and work side by side with their engineers, providing your expertise, which to help them with whatever problems that they're interested on. And at the end of that, they own the project. So they own all the information and everything. You basically work for them for 2 years. And out of that, you gain the opportunity to increase your network, provide great capability and help to our allies, and then to bring that collaboration, that information back with you when you turn to your home unit, that relationship to continue those collaborative opportunities in the future. So I love travel as well, and I've been really interested in this program. It worked out. You apply about a year and a half, I think, before you actually start this program. So I think I ended up applying in 17 or 18. I can't remember exactly, but I applied specifically to go to France as my number one opportunity. You have to order your opportunities, but I was particularly interested in France because of their superior capability in high temperature composites, which is what I was very interested in. And so I was able to reach out to some colleagues there, find a lab that was interested in hosting me. I put in my application and I got selected, which was amazing. And then as part of this program, if you go to a country that speaks a foreign language, you actually get to go to the Defense Language School for 6 months before they send you. So I went to Washington, D.C. at the beginning of 2019. I was there for 6 months at the Defense Language School, which is a whole nother experience of itself. I basically sat 7 hours a day, 5 days a week, one-on-one with just speaking French. So, and you do this for 6 months. And at first you don't know any French, right? At least in my case. And by the end, I was good enough to survive. Let's just say that. And so I learned French. We moved over there. I took my whole family and I started working in the ONERA, which is they call themselves the French Aerospace Laboratory, but they're essentially the equivalent of the Air Force Research Lab for France. They work primarily with their armed forces there. And I worked in their composite group doing some of modeling and simulation of high temperature composites. And I lived in Paris and rode my bike every day to work. And it was an amazing experience, except COVID. I got COVIDed in the middle of my opportunity. So although it was an amazing experience, the whole time I did spend a significant portion of that working from my apartment in Paris instead of at the lab in Paris, which was tough. I had to sit there and watch the Seine River flow by as I worked every day. So it wasn't all bad, but COVID did present some challenges while I was there.
Sure. And I mean, that's great to know that you could still get that experience, but have that unique take of having to work from home overseas. remote kind of.
Right.
But I will say, awesome you saw that opportunity, and I'm curious too with the 6 months you took in training. So I allegedly, I mean, I can claim on my paper took years of French training. How much is retained is a different story. But I took it in college. So is there any common phrases you still use now to either impress people or show them you speak French? Because my favorite is I still want to say I can play video games, which is so simple, but that's my favorite go-to. And they're like, "Whoa, this guy knows a lot of French." I'm like, "Sounds like I do, but it's not that impressive."
I love the greetings in French. Enchanté is,
Mhm.
pleased to meet you, and bonjour. And the great thing about my experience there is I'm still, even though I've been home over a year, I'm still meeting monthly with some of my French colleagues,
Awesome.
continuing some of those collaborations, and those meetings are still in French. And so,
So you're still fresh up on it. Yeah.
although I've been home a year, and it's kind of a little embarrassing for me because every month my French gets a little bit worse just because I only speak it once a month now instead of almost every day. I'm trying to
That's what I was
stay
gonna
up.
say. Or maybe I should bounce off you. I should do better. I always go with just an easy ça va when I say hello to people, but that's
Yeah,
very casual. So my
yeah.
mom takes a lot of French, and that's a her and I. Whenever we speak
Okay.
French, do that. But great to know you're still doing that though, still connected. And was there? So when you were over there, you mentioned they're very ahead in a lot of ceramics research, or at least some like high temperature research. What really stood out with that work? Like when you worked with your French counterparts, was their way to approach to research different, the way they connect with industry, or is it pretty similar to what we have in the U.S.?
France is obviously smaller than the United States, and so they don't have quite as diverse industry. And for that reason, you'll find, and I think it's similar in a lot of at least European countries, and maybe even elsewhere. A lot of their defense research is targeted not only to develop capability in certain areas, but also to directly support certain industrial partners within those countries that they want to, maintain. And so it was interesting to observe that a lot of the work that we did at Onera was done with students, which were directly funded through industry, which were directly funded in turn through tax breaks and stuff from the government. So as the government provided these tax breaks to industry, they would provide some of the student research and the internship opportunities to help keep their pipeline of fresh talent growing. And it was a really nice collaboration, anyways, between the government, the industry, and the government labs in terms of maintaining a constant pipeline of talent, but also transitioning technology from the government labs to industry, and just doing a lot of cool work. And so we have to operate within our acquisition rules and the FAR and everything, but I really did like how much they work directly with student interns that were directly sponsored by industry. And so I've tried to bring some of that back in terms of how do I set up teaming arrangements for projects instead of just focusing on, for example, an academic student project. It's nice to also do a academic student with an industrial partner on the side. And so it builds a broader team, but it also ensures a cleaner path to transition as we're developing some of these new technologies. Everything from electronics and computing to hypersonics to propulsion to even our aircraft structures is all, a lot of their capability is enabled by the material systems that we've developed that allow them to do all the crazy things that they could do today that they've never been able to do before. And so there's such a demand right now for talent to continue that push to advance, especially as we're competing at an international stage in terms of being able to maintain a competitive edge defensively and a competitive edge even commercially in terms of our latest technologies and stuff like that. A lot of that is driven by some of these latest material breakthroughs. And so my first advice would be is there's so many opportunities right now that it's a great field to go into. So if you have a hesitancy about worrying about being able to find a job, I just forget that and start thinking about what area of materials you're interested in. And that's, a whole nother challenge. But in terms of electronic materials, you may start with a more electrical engineering maybe route, or if you're more interested in structural materials, you may more start with a mechanical engineering route, or you may go straight into materials processing with a chemistry or material science background. Depending on your interest, there's so many different angles you can take a career. And so even if you're already in electrical engineering and you're wondering, well, how is that relevant to materials? It's very relevant, particularly to electronic materials. And so there's still lots of opportunities. You haven't eliminated yourself in any way, I guess would be my advice. I'd say if you're passionate about something, dive in. And right now there's just so many opportunities that it would be hard not to be able to find something. And if there's anyone interested, feel free to reach out to me. And we're always trying to hire good interns. So
Hey, we're going to keep that in mind then. So we have a direct connection with you, and of course, awesome opportunities, as you said. No matter what part of materials you want to go into, we can make sure, well, you're the right material for us. So thank you again. I'll definitely make sure to keep the French lessons in mind in case you want to bounce some ideas off each other. And of course, in future conversations, we'll see how your work has changed and evolved with the materials field. But we want to thank you, at least for today, for joining us and having such an awesome conversation. Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.